that we use to show the filament view was based on QEMU. And the QEMU virtualization system, emulation system, is not the best at floating point.
So here's that code from Megafish that was causing the problem. We see here that they have inserted some floating point instructions kind of early on in their binary.
Yep, and QEMU is not great with floating point, unfortunately. We actually found and fixed at least one bug beforehand, but we didn't catch them all, apparently. Software's hard. And so this was, yeah, it made it impossible to analyze with our visualization engine the binaries. Thankfully, that was not what the game was running on. The game infrastructure was completely separate from the visualization and was not based on something like that, but rather native hypervisor.
But it's kind of reasonable to maybe guess that some of the CRSs might have actually been using QEMU.
I would definitely assume that at least one of the teams had QEMU under the hood.
So
it's
if they
very
were
common.
performing some consensus evaluation on a replacement from Megafish, they're going to run into the same problem.
They're not going to analyze it. Yeah, absolutely. It's going to get here and it's just going to stop. You're going to see no more code at that point from the analysis engine if it tries to run it. And something like QEMU is really helpful because you can add data flow, you can add instrumentation kind of out of band where you can monitor for reads from the flag page. You can do a lot of nice things with that. In fact, that's why we're able to do some of those things with the visualization engine, how we can show the flag pages in yellow when we highlight the memory view, and some of those views are based on that underlying technology. So it's helpful to have, but if you can frustrate analysis, it makes it harder for your opponents.
And we saw some other forms of anti-analysis in the game too. This is a replacement from Galactica. What Galactica did that is interesting is they obfuscated the entry point to their program. They dynamically calculated it at runtime. So if you're doing any kind of static analysis on the binary, and you can see over here that no functions have been disassembled.
Because it starts at the sort of libc start, which is the entry point of the file, the CGC file format itself, which is similar to ELF. And so it starts at start, starts running down, and this is dynamically computed. And so when the program's running, it'll just compute it and jump right into main, no problem. But if you don't find that and you don't have some sort of kind of linear sweep to try to guess and identify where functionality is at, your analysis is going to be stalled out.
Here's another one that's kind of a favorite to look at. This is a replacement from Rubius. And Rubius figured out early on, I guess in some sparring rounds earlier in the competition, that there was a noticeable way to fingerprint that you're actually running on CGC infrastructure. And that's using the CPU ID instruction. Because the system had been modified to emulate one particular environment, the CPU ID instruction on the challenge infrastructure always returned the same exact value.
I mentioned earlier there was a hypervisor for the native system, and one of the side effects of that was to sort of fix the environment. So even as machines were swapped out or moved, that the running environment of CGC would be as predictable as possible. And so as a side effect of that, it had a hard-coded string for the text value. You can actually use the CPU ID instruction, and you get back a bunch of values. One of them is like a string, like the Intel whatever CPU, so it gives you the model of the CPU. And that information, they were able to not only detect during sparring, but then build in a system into their CRS so that it could detect if it was actually being running on that same hardware. And if you tried to run it elsewhere and you didn't exactly match that environment, they could behave differently.
Yeah, and so they went ahead and did. What we're looking at here is the same binary. Later on, after they detect that CPU ID, they decide if they're not running on challenge infrastructure, they go to this code here. And what they're doing here is actually what we've been calling a honeypot or a honey branch. We see some syscalls, and this one right here in particular, this is a receive syscall that's actually receiving onto the stack.
And it looks like a receive loop where it's going to loop around multiple times, reading kind of one byte at a time into the stack. If you're a competitor CRS, this looks just like a stack-based buffer overflow.
Yeah, a really simple easy one.
So hypothetically, you could see this, you could analyze it, and if you don't realize that this is never going to go here on the legitimate CGC infrastructure, you think, hey, that's a much easier flaw than anything else I might find, and you might throw a POV against this instead.
So we actually were hearing just about some dirty tricks or evasion techniques. Does Rubius employ any of these style of gameplay things?
It tries to make things difficult. It does, yeah.
Are there any specifics that you could go into?
Sure. I mean, you could probably take one of our binaries and try to open it up in a typical analysis tool, and it may or may not work.
Nice.
And if you want to run it, you probably ought to run it in an environment that looks an awful lot like the official system. It should only run where it's supposed to be running.
Yeah, this is a great technique. It actually worked pretty well. The dev team noticed it even during the game, and then I think did some analysis to see how effective it was as a technique.
And a number of other competitors. We saw submitted POVs from other competitors that specifically targeted this flaw. And so it will work if you test it locally on non-CGC infrastructure, but in the game environment, it would never actually run.